Okay, so last class we talked about solubility rates, electrolytes, non-electrolytes, non-polar, polar, ways that temperature affects the solubility of a gas and a solid. And we just learned about a lot of introductory terms in our new unit of solutions. Today we are going to be going over solubility curves. So this right here is a solubility curve. And if you notice, a couple of important things is looking at your x and y axis. So we have temperature, which is in degrees Celsius, and then we have solubility, which is in grams of the solute per 100 grams of water. Okay. So what we're going to be doing is we're going to be looking at our solubility curve and answering questions based off of what our curve looks like. So this first question says, what type of solution is represented by 50 grams of KCl in 100 grams of water at 75 degrees Celsius? How can you tell? So these three questions, okay, when it's asking us what type of solution, these three questions are referring to, is the solution saturated, unsaturated, or supersaturated? In last class we talked about these three terms and what they mean, but when you're looking at a solubility curve, okay, when you're looking at a solubility curve, anything that is saturated would be on your line. Anything that is unsaturated would be below your line, and then anything that is supersaturated would be above the line. So that is our way to tell based off of our solubility curve. So I'm going to read this question again and kind of walk through how we do this. We're talking about KCl. So this is our KCl, okay? It says 50 grams in 100 grams of water. This 100 grams of water right here, that's just referring to this, okay? It's just saying that's how much it dissolved in. So 50 grams at 75 degrees Celsius. So we have 50, and we're going to go 75. And when we do that, 75 up to 50, we end up right here. This is on our line, so we would say that this is saturated. How can you tell? On the line. Okay. Our next question is still referring to KCl, but this time 65 grams of KCl at 60 degrees Celsius. So I have 60 degrees Celsius. I'm going to go all the way up until I get to 65. And we can see based off of this, we're referring still to KCl, that this is above the line. So we would say that this is super saturated. How can we tell? Above the line. And our final question, still referring to KCl, what type of solution is represented by 40 grams at 80 degrees? So I'm at 80 degrees, I'm going to go up to 40. Now this one's kind of tricky because some of you might say that it's saturated. However, you have to make sure that you are looking at the correct line. This line right here is NaCl, but the question is asking us about KCl. So in reference to KCl, this would be below the line, which would make this unsaturated. Below the line. Okay? All right. Number 4 says, how many grams are needed to create a saturated solution of KClO3 at 50 degrees Celsius? So again, this saturated solution, if we go back up here what I was talking about, if we want something that is saturated, we need it to be on the line. Okay, and we are referencing KClO3. So I'm going to go to 50 degrees Celsius, and I'm just going to go all the way up until I reach the line for KClO3. When I'm looking at this, there is going to be a rough estimate, okay? I would say anywhere between 16 to 17 grams, okay? Number 5, at what temperature would 10 grams of KClO3 create a saturated solution? So this time, still we're referring to KClO3 in a saturated solution, which means we again want this on the line. However, this time we have 10 grams 10 grams, and so we're going to go across this way until we meet the line of where KClO3 is. Okay? KClO3, it says at 30 degrees Celsius, it would be saturated. A saturated solution of KClO3, just KCl was cooled from 70 to 30 degrees Celsius. How much solute will drop out? So what this is saying is we heat up our temperature to 70 degrees, okay, and we have a certain gram amount. And then as we cool it down, solute's going to fall out. So I'm going to go to 70 degrees. I'm going to go up until I reach KCl. That is about, it's a little bit below, it's not right on the line, it's a little bit below, so I'm going to say for 70, that's 49 grams. Then it says that it's cooled, okay, cooled to 30, so I'm going to go up, and this intersects with NaCl, but still the same thing, and I'm going to say that's about 38 grams. To figure out how much solute drops out, I just take 49 minus 38, and that gives me 11 grams. Now again, this is obviously an estimate. If you're one off here, then you'd be one off on their final answer. We have about a plus or minus range of about 1. All right. Number 7 says, which substance is a gas, which substance are solids? How do you know? So this is going back to what we learned in the previous day, when we were talking about with solids, if we want to dissolve solids, okay, so solids, whenever you increase the temperature of a solid, you increase the solubility, right? If I have a sugar cube and I want to dissolve it, if I increase the temperature, it will dissolve faster. However, with our gases, if we increase the temperature of a gas, you decrease the solubility. That was our example of a soda. So if you notice here on our solubility curve, every single one of our curves besides one, as you increase the temperature, the solubility increases. Ce2, cesium sulfate, however, does not. It's going the opposite way. You can see as my temperature increases, my solubility decreases. Looking at that, that is our gas. Okay. All right, which would mean all of the other ones are our solids. How do I know? This is my how do I know right here. That's my explanation. Number 8, if 10 grams of KClO3 are present at 90 degrees Celsius, how much more should be added to make it saturated? So, when I'm looking here, okay, it says if 10 grams of KClO3 are present. So I'm at KClO3 and I have 10 grams, okay? And I'm looking at 90, where my 10 grams is. So when I look here, okay, at 90 degrees on my line, it is 40 grams. Okay? So again, on my line I go up to 90, it's at 40. Okay? It wants to know if I already have 10 grams present, how much more needs to be added to make this saturated. This right here is what we want. This is a saturated solution. So if I already have 10, 40 minus 10 equals 30 grams. That is how much needs to be added. Okay, needs to be added. Finally, which solute is the least soluble at 0 degrees Celsius? Which is the most soluble at 0 degrees Celsius? So I'm going to look at my solubility curve. Okay, at 0 degrees Celsius, okay, if I go up, I land on KClO3. So that is going to be my least soluble, because that has the least amount of grams dissolved. My most soluble, I go 0 degrees and I'm going to go all the way up, and my highest one is CaCl2. That is saying that calcium chloride is going to dissolve the most solute at 0 degrees Celsius, whereas KClO3 is going to dissolve the least amount. There's lots of practice for solubility curves in your practice worksheet, so make sure that you do some of those. If you have questions, obviously it's in tutorials. Now moving on to molarity and dilutions. So molarity and dilutions, this is talking about concentration and calculations. So concentration, and I'm not talking about the concentration that hopefully you have right now as you're watching this video, but the concentration of the amount of substance per defined space. On a solubility curve, this was expressed in terms of grams of solute per 100 grams of solvent. Okay, that's what this was referring to right here. Okay. So when we begin to use solubility in working problems, we rarely express the concentration of a solution in terms of grams of solute per 100 grams of solvent like the solubility curves do. Rather, we use the concept of molarity. Okay, so molarity is the number of moles of solute per liter of solution. Okay, so you can see the various different ways to calculate molarity. Okay, you need to be familiar with both. Okay, so your units are moles, liters, or molarity. So if you are given milliliters, you must convert that. If you are given grams, you must convert that, and you can see that right there. And this is also found in your formula chart. Okay. So let's do a little word problem example before we get into this. It says, for example, if 2.0 moles of potassium nitrate is dissolved in enough water to make 1 liter of total solution, we would say that the concentration of the solution is 2 molar or 2.0 moles per liter. Or we could also say that we have a 2.0 molar solution. Molarity is the most common way of expressing concentrations of solution. When we have an increase in molarity, that means that the solution has become more concentrated. Okay, more concentrated. If we have a decrease in molarity, that means that our solution has become more diluted. And a good way to think about this is think about if you're making Kool-Aid or Crystal Light or even ramen. If you add, and you're making your Kool-Aid, if you have more flavoring than you do water, it's going to be more concentrated. Versus if you have more water than you do flavoring, it's going to taste more diluted. I'm sure a lot of people, you've tasted like a lemonade or something and you taste it and you're like, ooh, that's super duper sweet. It's going to be more concentrated. Or you take a sip and you're like, ooh, this kind of tastes watery. That would mean it'd be more diluted. So those are just some concepts. Now we're going to actually do some calculations. So this first one says, what is the molarity of a 2.5 liter solution with 15 moles of solute? So we are going to be using our guess method, which we have used before. This is where you write the given, the unknown, what you're trying to find, your equation, you substitute, and then you solve with answer. Okay? So again, let's write down what we have. What is the molarity of a 2.5 liter? So we are given 2.5 liters with a 15 moles of solute. So 15 moles. It wants us to find the molarity, so we're finding the molarity. Okay? Now, just to double check with our equation is molarity equals moles over liters. And if I look, my unit is in moles, good. My unit is in liters, good. So, when I look at this, I have, trying to find molarity, I have 15 over 2.5. Okay? When I divide these, I get 6. Now, with sig figs, I need 2 sig figs, so 6.0, and my unit is molar. Okay? Each box is worth 1 point, so I'd get 1 point here, 1 point here, 1, 1, 1. Total of 5. Next one, how many moles are in 0.75 liters of a 2.0 molar solution? All right, my given, I have 0.75 liters and a 2.0 molar solution. Okay, my unknown is moles. And my equation, I have 2.0 molar equals moles over 0.75. Now, I know sometimes people get confused on should I multiply, divide, what am I doing? So I'm going to, down at the bottom, just show you a little trick. We have a little triangle. I'm sure you've seen this before in math, maybe, hopefully. Okay, the top is our moles, molarity, liters. So what this is saying is if they're over each other, you divide. They're next to each other, you multiply. You can also manipulate your formula up here if you want. So what this is saying is I'm looking for moles, but I'm given molarity and liters. So all I do here is I multiply these two. Okay, so 2.0 times 0.75, and I get 1.5 moles. And actually, I messed up. This should be here. This should be molarity equals moles over liters. So when I do that, I get 1.5 moles. All right. Do one more. Or actually, I can do maybe a couple more. How many milliliters are in a 0.45 molar solution containing 0.75 moles? So I have 4.5 molar, 0.75 mole. And I know it says how many milliliters, but I can't find milliliters with this equation. What I can find is liters and then convert to milliliters, right? My equation, molarity equals moles over liters. Plug this in, 4.5 molar equals 0.75 mole over liters. If I look at my triangle down below, if I have moles and molarity, I divide these two. When I divide these two, I end up with a repeating decimal of 0.16667. Okay, and this is liters. That's not my final answer. So what I have to do is, you can come down here for room, and I wouldn't round ahead. I would just take this, and you have this conversion. It's in your chart, okay, and you end up with 167 milliliters. But we need 2 sig figs. So with 2 sig figs, this rounds to 170 milliliters. So a question like this, you can notice it's worth more points. 1 point, another point, another. You get 1 point for showing here, and then your final point. Okay? Let's do one more. How many grams of C2H6 grams are in a 2.0 liter solution at 5 molar? We are given 2.0 liters and 5.0 molar. It's asking for grams, but we can't find grams with our equation, but we can find moles and then convert to grams. Okay? Molarity equals moles over liters. 5.0 molar equals moles over 2.0 liters. These two are next to each other, so we multiply those. When we multiply them, we end up with 10 mole. Okay? I have to convert this to grams. And when we go from moles to grams, one step, molar mass. Okay, so 10 moles C2H6, 1 mole C2H6. I have to calculate my molar mass, okay? So 2 times 12.01, 6 times 1.01. When I add these two together, I get 30.08 grams of C2H6. When I multiply these, I get 30.8. Okay? I need 2 sig figs. And this one's kind of hard. It's kind of weird, so I'm not too worried about the sig figs here. We would round this up to 301 grams of C2H6. Okay? Molarity. Next up we have dilutions. Okay, dilution, okay, is the process of making a solution less concentrated This is usually done by adding more solvent to the solution. So we're going to be looking at these two pictures, and it wants us to figure out which of these solutions is more concentrated. So if you look here, you can see that you have the same amount of particles, but what you did here was you added H2O. Okay? There is a high molarity here and a low molarity here because it's diluted. Because when you increase the molarity, your volume decreases. Whereas over here, when you increase the volume, your molarity decreases. So they're inverse of each other. So if I look here, the one that is more concentrated would be A. The one that is more diluted, B. So we can use molarity in dilution problems as it's the most common way to express concentration. When we add more solvent, again normally water, we decrease the concentration of the solution, which decreases molarity of the solution and makes the solution more diluted. Okay? Now, on your formula chart, your equation looks like this. M1V1 equals M2V2. It's the same thing. The reason we have it like this is for you to remember voom voom, okay? It's written that way. Now, one thing to just kind of think about is if I ever were to ask you a question about how much water is added, we will get to that in number 3. Okay, when you need to figure out H2O added, that is the difference of volume 1 and volume 2. Okay, so just keep that in mind. Alright, so let's do a problem. It says 4.2 liters of a 3 molar solution is diluted to 10 liters. What is the new molarity? So this time we have 3 givens, and because we know our equation is M1V1 equals M2V2. When it says what is the new molarity, that's referring to M2, which means I have M1, I have V1, and I have V2. So now you have to figure out what is what. Now, a helpful way is when you see 2 numbers and of A sandwiched in between, that is referring and saying that those 2 are together. Okay? So my M1 is 3.0 molars, and my V1 is 4.2 liters, and then it's diluted to 10.0 liters. Another way to help you is if something is diluted, that means you have added H2O, right? So that means that you've added H2O, so that number should be higher. Whereas when I solve for my second molarity, it should be lower, because if we add more water, when you increase the volume, molarity decreases. So now I plug this in. 3.0 times 4.2 equals x times 10.0. When you plug these in, you get 1.26. You need 2 sig figs. 1.3 molar. Alright, number 2. 0.25 liters of a 12 molar solution is diluted to 10 molar. What is the final volume? So that's nice because it's telling you that you need to find V2. M1 V1 equals M2 V2. So I'm given M1 V1 and M2. My M1 is 12 molar. My V1 is 0.25 liters. And my M2 is 1.5 molar. So now I can plug in what I have. 12.0 times 0.25 equals 1.5x. When I plug this in, I end up with 2.0 liters. Okay? And you can see my first volume was 0.25, second volume was 2.0. Which means that's good, that it should increase. Now, it says use example 2 to calculate the additional volume added. So the additional volume right here, H2O added. It tells you to take the difference of V1 and V2. So my V1 was 0.25 liters. My V2, which was right here, 2.0 liters. So when I take 2.0 minus 0.25, I get 1.75 liters. Okay? And that is solubility curves, molarity, and dilutions.